In this video, we're going to fit modern Linux kernel inside of this floppy disk. And we're going to use this floppy drive to boot this Sony VAIO from 1999. We're going to start by downloading the kernel source code. But before that, make sure you have the dependencies set up. If you don't, I made a couple of scripts here to set up everything you need for this video. And this assumes Debian, and Debian is what I'm going to use in this video as well. All these do is just install a bunch of packages from apt. Over here on the kernel official website, I'm going to go here to stable and grab the tarball. Now if you go here to downloads, you should see it over here. I'm going to extract it with tar-xf, extract file. And I'm going to move this to a new directory I'm going to work in. So I'm going to call this directory distro. And I'm going to move it over here. Let's just call it Linux. Okay, over here I'm going to run make and then tinyconfig. Now what is tinyconfig? So I'm going to run here make help. And here you can see tinyconfig. Configure the tiniest possible kernel. Remember, our goal here is to fit everything inside of a small floppy. So this will help us achieve this goal. Make tinyconfig. And now I'm going to run make menu config. This will open a visual menu, which will let me further customize the kernel. First thing I'm going to do is I'm going to enter general setup. And I'm going to scroll down here and enable initial RAM file system. This is important because this is a mechanism that will load our user space. And over here I'm going to disable everything except LZMA. This is the compression we're going to use in the user space file system. We're later going to build that. Okay, afterwards I'm going to scroll down more. I'm going to enter this option over here, configure standard kernel features. And here I'm going to enable support for printk. This is useful to enable so you'll see all the kernel boot messages. Okay, now I'm going to exit. And I'm going to go here to executable file formats and enable ELF binaries so we can start binaries from user space. Now I'm going to exit. And I'm going to go here to device drivers and scroll down. And I'm going to enter this option over here, character devices. I'm going to enable TTY. So we'll have a proper console. Now I'm going to exit, and that's it for the configuration. So I'm going to exit completely and save everything. Okay, and now I can start the build. But first of all, I want to know how many cores I have. So I'm going to run here nproc. I can see I have 20 cores. So I'm going to run make, and I'm going to split this to 20 jobs using the -j flag. Okay, and we can see the kernel built successfully. BusyImage is ready. So what I'm going to do is let's first of all see how big this is. So I'm going to run here ls-lh on this. You can see it's 749K. I'm going to copy this. I'm going to call it BusyImage. I just put it over here in the distro directory. Okay, and we have the kernel ready. Now it's time to create our user space. For this, I'm going to open a new folder here. So I'm going to call it fs. And I'm going to get another program called BusyBox. BusyBox is basically a bunch of standard Unix utilities all in one binary. And you can configure it to include whatever utilities you want. So over here on the official website, and I'm going to put links in the description, by the way, to everything in this video. I'm going to scroll down and click here on source control. Here I'm going to copy the git clone command to get the BusyBox repository. I'm going to clone it over here. And first thing I'm going to do is I'm going to run make all no config. This will basically disable all the utilities of BusyBox, so later we can handpick whatever we want. Okay, now I'm going to run make menu config, so we can interactively configure BusyBox. Okay, first thing we got to do is a couple of stuff in the settings. So here I'm going to support files bigger than 2 gigabytes. I'm going to build a static binary. This is important because I don't want to be reliant on a libc. I want my binary to be self-sufficient. Also, since we're building this distribution for a 32-bit computer, and I'm currently on a 64-bit, we need to supply a cross-compiler prefix, so it won't build a 64-bit program. The prefix of the 32-bit compiler of GCC is I686, and then you can just press here tab. And this is it. So I'm just going to copy this. And by the way, if you press tab another time, you can see all the utilities. And here's GCC, for example, for this target. And this is one of the dependencies. You'll see this in the dependency scripts. So I just copy the prefix and I'm going to press enter on this option over here. Okay, that is it for the configuration over here. So I'm going to exit. And now we can start enabling utilities we want. So first, let's go here to core utils. I'm going to add cat. Let's add date as well. Echo. And ls. Now I'm going to go to editors and enable VI. And also I'm going to go down here to shells and enable ash. So I'm going to have a shell as well. Now I'm going to exit and save the configuration and build it like before, make with the number of cores on my computer. Okay, now we should have BusyBox over here, so let's take a look. This is BusyBox, and this is a size, it's quite big, but we're going to compress it as part of the initial RAM file system. So I'm going to copy this to the distro folder. Now let's go back to the distro. Let's see what we have here. So we have BusyBox over here, and we have the image of the kernel. What I'm going to do is I'm going to move BusyBox into the FS folder. We'll start preparing the user space file system. So this is FS currently. What I'm going to do is I'm going to create a hard link with ln to BusyBox. And I'm going to call it sh. So the target is going to be BusyBox, and the name of the link is called sh. And now let's take a look at ls. And now you can see we have here two files, BusyBox and sh. And sh is just a hard link to BusyBox, so they're basically the same file. Now, why did I do this? I'm doing this because BusyBox changes the way it acts according to the file name. So if the file is named sh, BusyBox will act as if BusyBox is invoked like this, BusyBox and then sh. Which you can see, of course, brings up the built-in shell, ash. If BusyBox is invoked, for example, with date, which is also a utility we added, it'll show the date. Now you can see that because I made a link called sh, I can just invoke sh, and this will also load the shell. And this is useful because we're going to tell the kernel that we want to load sh as the initial process of the system. Okay, now I'm going to just pack this inside of an initramfs archive so the kernel can load this. So what I'm going to do is I'm going to first utilize the find command. We just have here two files, so it's kind of funny, but still. This is what find is going to tell us. And I'm going to pipe this into the cpio command. Now let's take a look at the man page for cpio. So first we're going to use the create option. cpio, by the way, creates an archive that the kernel can read. This is the archive of the initramfs, of the file system of user space. So I'm going to pass this to create a new archive. Then -h. Let's take a look at that. I need to specify the new C format, which is the format the kernel supports. Okay, and afterwards, this will output the new archive, so I'm just going to redirect this. I'm going to call it init.cpio. Okay, now if we take a look over here in the distro directory, here's the archive of the user space. Now I'm going to compress it using LZMA. Remember that we added support for LZMA into the kernel. So this is the compression we're going to use for the initramfs. Okay, now let's take a look at the sizes. Now before I'm going to set up the floppy disk, I'm going to try booting this with a virtual machine. And for this I'm going to utilize the QEMU emulator. I'm going to use the kernel parameter and pass in the BZ image, the image of the kernel. I'm going to use the initrd parameter to pass in the initramfs. Also, I'm going to use append to append a kernel parameter. I'm going to tell the kernel that the rdinit, the init process that I want to load as the first process of the system, is going to be sh, because we want to load the shell as the first process of the system. Let's see if this works. Okay, and we have a shell here. That's pretty cool. Also, we can load VI, for example, so BusyBox and then VI. And this works. Okay, so if I run the command lsblk, you can see over here the floppy disk. This is an SDC, and this is a size over here, 1.4 megabytes. And first thing I'm going to do is I'm going to use the makefs command and make a FAT file system. Initialize a new FAT file system on the floppy. Now at this point, you should hear the floppy spinning. By the way, you can do these same steps just with a USB flash drive. It'll also work. Okay, and after running this command, I'm going to install the syslinux bootloader. For this, I'm going to use the command syslinux -- install, and then the device. And this is the bootloader that will be responsible for loading the kernel and the initramfs into memory, and finally passing control into the kernel. Okay, now I'm going to mount this device into MNT. And we can see how it looks so far. So you'll see here a couple of files related to syslinux bootloader. And now we're going to add the kernel and the initramfs. So first of all, let's copy the kernel. Afterwards, I'm going to copy the initramfs. And finally, I'm going to unmount. Now I'm going to just run here sync to make sure everything is in sync with the floppy drive. And only when you see that the floppy drive is not spinning, I'm going to disconnect it from the computer. And now it's time to test this on real hardware. Okay, now we're going to test this floppy drive with this Sony VAIO here, and let's see if it boots up correctly. Okay, and you can see now syslinux has loaded up, and it's asking me what I want to boot. So I'm going to tell it to boot Linux. I'm going to specify where Linux is, which is in BusyImage. So I'm writing here /BusyImage. And then I'm going to tell it where the initramfs is. So I'm going to type in initrd equals /init.cpio.lzma. Finally, I'm going to say rdinit, so the init process of our system is going to be /sh. And now I'm finally going to press enter, and it's going to boot up everything. And you can hear the floppy spinning as it loads Linux from the floppy disk. Okay, now it's loading the initramfs from the floppy disk. This is still the bootloader. Linux is still not given control. Okay, we can see now Linux has loaded successfully and BusyBox shell is up and running. Now we can fire up VI, for example, so /BusyBox and then VI. And here we have VI working. Let's exit. Now I'm going to try BusyBox and then date. And finally, let's try BusyBox echo.